Welcome everyone to another seminar of Physics Latam. Today we are very happy to have Professor Veronika Hubeny with a talk on recent developments on holographic entanglement entropy. Veronika is a theoretical physicist, currently professor in the Department of Physics and Astronomy at UC Davis and a founding member of the Center of Quantum Mathematics and Physics. She obtained her PhD in 2001 at UC Santa Barbara, following two postdocs at Stanford University and UC Berkeley. From 2005 to 2015, occupy a senior position at Durham University. Her research interests lie mainly in areas of string theory and quantum gravity. Much of her past work has been set in the context of gauge gravity duality and black holes. More recently, she has been focusing on the fascinating connection of quantum information theory, in particular on the relation between entanglement structures and emergence of the dual space-time. Please remember to raise your hand at any point if there is any question during the lecture, and now I leave you with Veronika. Please go ahead.
Okay, thank you very much. And thanks for organizing this school. It sounds like a wonderful idea, and welcome everyone. I hope that we can have it very interactive, so feel free to unmute yourselves and ask anytime. So I decided that since you had this already a great preparation about gauge gravity duality and about entanglement or entanglement entropy, especially both consolidated in Rockstock a few weeks ago, I will focus on sort of two more recent developments that are sort of orthogonal to what you heard before. One is what happens when you have sort of time dependence in fully general situation, and the other is what happens when you want to talk about multiple systems. So as you'll see, they're sort of quite interrelated in the context of what I'll be telling you about. Okay, so let me just motivate why one should be interested in this. Oh, let's see. And let's see if I can, there we go. Okay, so let me start with a bit of the motivation. All right, so it all harks back to sort of emergence of space-time. Space-time and classical GR dynamics we understand very well, but it's a notion that it's not described in some fundamental way. It predicts some breakdown by curvature singularities and so forth. And so we want to understand how it emerges from some more fundamental fully quantum theory. And if you think about it, it's actually quite remarkable. The world is inherently quantum mechanical. And so what I want to, the sort of mindset I want to have for this talk is not to ask, how do you put quantum corrections to GR, or how do you make GR consistent with quantum mechanics, but rather, how does the classicality emerge from quantum mechanics that sort of leads to this beautiful GR dynamics? And so I'll focus in the entirety of the talk on just classical bulk space-time. And I say bulk because the great toolkit to address this question is to use holography, where we have, on the one hand, string theory, which contains gravity. So we have in a special limit of the string theory, we do have this GR dynamics. But on the other hand, we have a non-gravitational quantum field theory, a strongly coupled, highly quantum many-body sort of system. And so we want to use that framework to ask how does this space-time emergence happen there? And in particular, from the non-gravitational theory, how does that CFT encode the space-time, the bulk geometry? And early on, people utilize very heavily, and even to this day, people utilize heavily sort of the symmetries that the vacuum has. The pure ADS is related to the vacuum in the CFT, and there's lots of symmetries, and you can sort of utilize that. But what I instead want to do is I want to go in completely the opposite direction and consider the bulk in its full generality. And so I want to consider a general time-dependent bulk spacetime without sort of any particular symmetries. And why do I want to do that? Well, the primary reason is that it's really reveals the actual physics that's at play in the underlying the mapping between the two sides. Of course, that requires us to talk about constructs which are meaningful, so which are fully generally covariant, and therefore geometrical constructs that don't depend on some extra baggage that we didn't put in, like a choice of coordinates or something. Okay, so this is, of course, in this regime, we don't have anymore the power to calculate explicitly the various constructs, but we have, on the other hand, we can utilize the various powerful GR theorems that then allow us to make, as you'll see, lots of progress. Okay, so that's the bulk side. Now, what do we want to do in the correspondence? Well, over the last decade, we had many hints that actually entanglement somehow plays a crucial role. Some slogans you might have heard is, entanglement builds bridges, or holds space-time together, or ER is EPR. We want to understand what that actually means. What is it about entanglement in the CFT, or more general framework, that actually gives us a classical bulk spacetime in the dual. All right, and because the CFT is very, is a multipartite system, infinite partite system in some sense. So far, while we have been talking mostly about sort of bipartite entanglement, just because that's the best understood object, really what we want to do is get a better sense of what's the sort of the multipartite entanglement structure. And so one wants to understand this multipartite entanglement structure for CFT states that encode classical bulk spacetime, but in this fully, time-dependent situation. Okay, so that's the motivation. The motivation at getting at how does the spacetime emerge from some more fundamental theory has receded to just considering holography, considering a special corner of holography, which describes a bulk geometry, a classical bulk spacetime, but arbitrarily time-dependent. And it wants to probe that by looking at entanglement that sort of knows about multiple subsystems. So what I want to do in this talk, I want to break it up into two main parts. And I'll try to take a break if I have time after the first part. So one is to discuss this covariant construct, and in particular for holographic entanglement entropy in the bulk. And the second part is to sort of talk about how we discern the multipartite entanglement and what are the relations between entanglement entropies of the different types of different subsystems. And I hope I'll have still some time to have some discussion, but if I see that I'm running out of time, that I'm going too slow, then I'll skip some things in the later part. Okay, so so in the first part, I'll first start talking about just the spacetime, how do we see spacetime in holography, and then describe the very covariant constructions for the holographic entanglement entropy. I'll review for you the HRT prescription, then talk about two other closely related ones, and then talk about much more recent work with Matt Hedrick about the so-called bit threads. And then in the second part of the talk, I'll define entropy space and so-called entropy cones, and sort of the key quantity that simplifies the description and seems to be very powerful, the so-called pattern of marginal independence. And then, if time allows, talk about how we can repackage these relations, these inequalities between holographic entropy for various, entanglement entropy for various subsystems. Okay, so let me start with the first part. Actually, let me pause to see if there's any questions about the motivation. Okay, great. So then let me start with the first part. So space-time in holography, well, we know that the bulk has extra direction. It's higher dimensional than the boundary, than the CFT, which you can think of as some sense in living on the boundary. And in particular, the extra one direction is that's the most obvious one, is the radial one. And in the early days, people got intuition from the ADS geometry to describe how does this radial direction emerge. So this goes under the name of UVIR, or scale radius duality. So if you look at the ADS, so this is the famous Subcan picture of ADS, but I'm viewing time running up, radius running sideways. If you look at the spatial geometry, because after all, we just need to discuss the space to see the radial direction. In the spatial geometry has this Poincare disk structure, which is very nicely illustrated by this Escher picture, where each of these fish is the same proper size. You have infinitely many of them before you get to the boundary. And you want to ask, how does a given point in the bulk, that's at some radius, how is that described by the CFT, which doesn't have this radial direction, which is just living on the boundary in this sense. And we learned that, well, it seems to be somehow related to the scale of the corresponding excitation or description, depending on how you're describing this point, in the CFT. Okay, and that of course fails as you go deep in the bulk. It holds asymptotically, but nevertheless, it gives us lots of good intuition about, insight about what happens in dynamical processes. So for example, if you, in the space-time, if you drop a particle from near the boundary, it's going to follow some, let's say, geodesic. It's going to slosh around. It feels this potential well of ADS. So in the bulk, it's going to go from near the boundary down. And so in the boundary, what that corresponds to is you have some short scale excitation that spreads out. Of course, that's very intuitive of what should happen in the strongly interacting CFT. So both sides made sense, but they're related by this very nicely. Or if you have a black hole in the bulk and the particle falls in, then you immediately realize that as you're coming close to the black hole, the description would spread out over the entire boundary, and you need something more to describe what happens close enough or even inside the black hole. And another nice thing that sort of already comes out of this picture is that, well, there isn't a sort of a unique region here that describes a bulk point. It could have been something else. That's also very nicely illustrated by this Escher picture, which is what eventually led to the insight that described the mapping in terms of the quantum error correction. The bulk acts as somehow a quantum error correcting code. Okay, so that's when you have all these symmetries. Now what happens in general? What happens when you have some arbitrary, asymptotically ADS, but arbitrarily time-dependent, non-spherically symmetric space-time? Okay, well, in general, we don't even know what we mean by the radial direction. You see, there is no, because we don't have the spheres, we don't have spherical symmetry, there is no unique notion of what does it mean to go, radially out from some origin. In other words, you can pick any point will serve as good as an origin as any other, and you don't have any, killing fields in the space-time to single out a special one. Similarly, you don't have a notion of what does it mean to be at constant time in the bulk, because again, there is no time translation symmetry. So you can take many slicings of the space-time, but there isn't a unique one. And so when you ask, for example, what region in the bulk would correspond to some slice on the boundary, well, there are many candidates. So here is again the Subcan picture. Here would be a t equal to 0 slice. So by the way, the boundary itself, because this is asymptotically ADS, the boundary has a metric of Einstein's static universe. It's static. So in the boundary, it actually does make sense to single out time being the one that's that's determined by the killing field, the time-like killing field, orthogonal to the spherical symmetry of the boundary. Okay, so there's a well-defined notion in the boundary of what is, constant time slice, but in the bulk, which is time dependent, you can have many distinct Cauchy slices that end on the t=0 boundary slice. And I can call that foliation by Cauchy slices my time coordinate for the bulk. And so constant time in the bulk doesn't mean anything. Now, you could take, for example, a slice, a codimension 1 slice of the bulk that maximizes the proper volume, subject to the boundary condition that it ends on this t=0 boundary slice. So that's a covariant construct. It's a geometrical thing. It maximizes the proper volume. So that's fine. And in fact, that subject to energy conditions and so forth, it actually exists and it's unique. All right, so that's good. But there are many others. And in particular, if you want to ask, for example, so suppose we declare, okay, this volume maximizing slice, it's the dual of the t=0 slice. Well, then we have the awkward situation that if you have a geodesic between 2 points at time =0 in the bulk, it's not going to lie generically on this volume maximizing slice. Even if it's tangent somewhere, it's going to go off because it's the thing that determines geometrically where the geodesic is and where the volume maximizing thing is depends on different things. So it's not going to, this volume maximizing thing is not going to be geodesically complete. All right, so if you have geodesics, they're not going to stay on the slice. And in fact, what happens is that the envelope of all of the geodesics that are anchored at the single time actually generically gives you a codimension 0 space-time region. Okay, so if for some reason you were after describing just geodesics, you would say, well, maybe this region is the dual of the t=0 slice. Or you could take higher dimensional extremal surfaces that end at t=0. Okay, all of these are covariant constructs. Depending on what you're after, you might decide that one is more natural than the other. And of course, you can combine them. You can take the union of all of these. The maximal thing that you can meaningfully take would be this Wheeler-David patch, which is just a domain of dependence in the bulk of any slice, let's say this one or any other one that ends at t=0. That's fine. That looks like a very nice construct because it's really constructed by null congruence going from this t=0 slice in both directions. It's the interior of that. But actually, this set is also not, well, as nice looking as I have drawn it, because you have these null geodesics coming and intersecting without spherical symmetry. They don't intersect all nicely at the tips. They intersect somewhere else. And that causes these caustics and crossover seams. So this surface is actually very kinky, very non-smooth. Nevertheless, that's sort of a maximal candidate. So this was all just a detour to illustrate that once you relax the symmetries from, say, pure global ADS to generic situation, you suddenly get many options. And general covariance, having constructs that geometrically are supposed to describe something physically meaningful on the boundary, is a necessary but definitely not sufficient requirement. What you have to supplement it by is, more physics to tell you what is it that you're really after. What is the physics of the boundary thing you're trying to map, and mimic that in the bulk. All right. Let me again pause to see whether there are any questions before I start describing the holographic entanglement entropy. Okay, good. All right. So again, the context in the space-time emergence is to use the holographic entanglement as a diagnostic of the bulk geometry, and in particular, as you have heard very nicely reviewed from Rob, a very useful measure of entanglement is the entanglement entropy, which I'll review in a bit later, but which, as you all know, is a von Neumann entropy of the reduced density matrix pertaining to a given subsystem. So I'll show the definition later on, but let me now talk about the bulk joule of that. So it was already known since 2006 from the proposal of Ryo and Takayanagi, the so-called RT prescription, that then if you have on the boundary specify a subsystem, a spatial subsystem, let's say we call this a region A, so this is just a Poincare disk, just a spatial slice. In static situation, where we really can concentrate just on a spatial slice because that's well defined, the entanglement entropy of such a boundary subsystem is given by the area, the proper area of a minimal surface, well, quarter of the proper area of the minimal surface in Planck units. The minimal surface is one which is so-called homologous to this region A. Okay, it ends on the boundary of A, which is the entangling surface. And then you can think of it as taking any surface S in the homology class of A. So that means there's some region here between the surface and A that doesn't have any other boundary. Okay, so its only boundaries are the surface and the boundary region. So that's what this homology means. And you take the global minimum out of all the global minimum of the area out of all the possible surfaces you can have. Okay, so that is very familiar to all of you. Now, if you have a time dependence, then this no longer applies. Why does it no longer apply? Well, what we were doing tacitly here, this was a covariant construct in the following sense. If you have enough symmetry, there's a well-defined constant time slice. It's a time reflection symmetric slice. And you look only within that time reflection symmetric slice. In that Riemannian geometry, you really have a globally minimal surface here. And therefore, that's a well-defined thing to do. Now, if you have a general time-dependent situation, as I said before, there is no unique notion of constant time slice. So you don't have a Riemannian geometry where you could define this minimal surface. And so if you take the full bulk spacetime, because of the time direction, you can make the areas arbitrarily small by wiggling the surface in the, locally piecewise null directions. Okay, so the minimality here no longer makes sense. But what does make sense is to consider just an extremal surface. What does it mean, extremal? Extremal means it extremizes the action, which is just the proper area of the surface. So if this were three-dimensional as I'm drawing, this would be the extremal surface is just a space-like geodesic. If it's higher dimensional, then it's a space-like codimension 2 surface whose area under linearized variation stays the same. Okay, it's saddle point of the area region. So that's what we mean by the extremal surface. Now you see, you still have a minimum here. It's you take the minimum over all the extremal surfaces in the given homology class. So here you're really finding an extremal surface, but there could be multiple ones. In pure ADS, there is only a single one. There's a unique one. But in more complicated geometries, you can have multiple ones. And so the multiple ones can have different areas, and then you take just the one with the smallest area. Okay, so that gives you the entanglement entropy. That's the so-called HRT prescription, which we described already very soon after the RT prescription. All right, so now, before I go on, I'll tell you in a moment two more very similar prescriptions where we sort of break down this extremization into two steps. But let me take the excuse to take a slight detour into describing for you or reviewing for you two constructs that you probably keep hearing mentioned quite often, which is the notion of the causal wedge and the entanglement wedge. The entanglement wedge will be the thing that's associated with this extremal surface, but the causal wedge is a simpler construct because it only relies on the bulk causal structure. And we'll contrast what these look like. Of course, in pure ADS, they're the same thing. For simplest situation where you have a spherical regions on the boundary, but in general, they're different. So I want to just explain that before going on, just to give you a little bit of practice of what sorts of things you have to worry about when you do have a general time dependence. Okay, so you start with the boundary. So here we imagine this is a boundary. There will be bulk in this direction. Time runs up and space runs horizontally. And I'm sort of trying to draw this in perspective in sort of 3D. So on the boundary space, at constant time, on the boundary space, you single out some subsystem A. Okay, so this is some spatial region, which I'm drawing as this interval. Now, what's the most primal thing you can do to describe a bulk region? So here will be bulk region that's somehow most naturally associated with knowing everything about this region A, in particular with knowing the reduced density matrix of this region A. What sort of thing could we expect? Well, on the boundary itself, once we know initial conditions in A, we can determine the physics inside this entire domain of dependence on the boundary. So that's what I mean by the subscript boundary. Okay, the domain of dependence A within the boundary spacetime. Okay, so we know, if we know the reduced density matrix here, we know the physics in this entire region in the boundary. Now, what can that correspond to in the bulk? Well, if we want to influence something in the bulk, that influence would be within the future set of any point in here, so that would stretch up. If we want to be influenced by the bulk, it would be within the past set. And so the natural thing to do would be to consider the intersection of what all can influence this physics in the bulk with what all can be influenced. Okay, so this is some region like this. And this is the region that we call the causal wedge. Okay, so if you want a formula for the causal wedge, it's the intersection of the future and the past of this domain of dependence on the boundary of our region A. Okay, so you can think of it as being spanned by the set of all causal curves in the bulk that start and end on the boundary within this domain of dependence. The spirit of it being to say that, well, this region should be particularly easy to describe, knowing A, because you can construct a test observer in the region A, you can send them into the bulk, and they can collect the information about any point here, about the geometry, and then come back and tell you. Okay, so in that spirit, this is a sort of natural region that's associated to the reduced density matrix, and it didn't rely, but it relied on the geometry to the extent that it relied on the causal structure, but it didn't rely on any more than the causal structure. It only needed to know what's causally separated from this domain of dependence. On the other hand, the entanglement wedge does rely on the bulk geometry in the following sense. You do need not just the causal structure, but the geometry to tell us what the extremal surface is. So here's the same setup. We have our boundary subsystem. We know the reduced density matrix. But now let's start from also recognizing that we know the extremal surface in this homology class that ends on the entangling surface of A. So we can construct this homology region. Okay, that could be any slice between the extremal surface and here. Okay, there is no notion of what time it is at, but it's pinned here. And then what we can do is we can ask, well, so suppose this is the thing that naturally corresponds to A, what all in the bulk would then be determined by that? Well, it would be its bulk domain of dependence, which is constructed by sending this null normal congruence from this extremal surface inward towards the region A. Now, in general, this extremal surface pokes out, further than this rim of the causal wedge, and so these null generators will start intersecting by gravity, by Ricciardo's equation that assumes a null energy condition. So they will start intersecting, causticking, and intersecting, and so by the time. And of course, if you want to ask the domain of dependence, if you follow these null generators, these null geodesics beyond the intersection, that's no longer inside the domain of dependence. The domain of dependence boundary is generated by these null geodesics, but it doesn't go past. And so this region caps off, and it caps off precisely at this boundary domain of dependence of our region A. And this is the region that we call entanglement wedge. Is the set of points in the domain of dependence of this homology region, or set without all this baggage of the homology of the slice. It's the set of bulk points which are space-like separated from this extremal surface in the direction of A. So the extremal surface partitions the entire bulk into 4 regions, 2 that are time-like separated to the future and past of the extremal surface, and 2 which are space-like separated towards A and towards A complement. Okay, so this partitioning, that's what the entangling surface would do for you in the boundary. The extremal surface mimics precisely that in the bulk. Okay, so if you have just pure ADS geometry and a single interval like this, it would turn out that these 2 constructs precisely coincide. But in general, they don't. In general, you can show very easily that the extremal surface must lie outside of this causal wedge. And in fact, even in pure ADS, even in pure ADS3, if you have more complicated regions, that also can be the case. So here's an illustration where you have the region A composed of 2 intervals, here and here. Now, what we're prescribed to do, okay, so this is the space-time picture and this is the spatial picture. The spatial picture just illustrates the projection of null generators onto the Poincare disk. But you have 2 possibilities for what's a minimal surface in this spatial geometry that corresponds to these 2, that's in the homology class of these 2 regions. One possibility is this purple set of curves, which are just in the homology class of A1 union A2, and they're unions of these individual surfaces. That's one candidate. Another candidate in the same homology class is the set of these 2 surfaces, the blue ones. And depending on which one has smaller area, that's the defining one for the HRT prescription. So in particular, if you make this gap smaller than the volume spanned by the regions in this 3-dimensional context, then it turns out that this would be the correct one. On the other hand, this purple thing is what will define for us the causal wedge, because the causal wedge is given by the generators, the null generators that come from the tips here of the domain of dependence. Oops. Okay, so here we see an example where we would have a causal wedge, which is generated by these orange things, inside the entanglement wedge, which is bounded by these blue generators. Same thing in the past, I just didn't want to clutter the picture. So here you have an example where the entanglement wedge contains the causal wedge, which, as I said, is always the case that you can prove assuming the null energy condition. All right. So from just this type of reasoning, you can conclude various things without relying on specific geometry. So, for example, the causal wedge, if you change the region A, the causal wedge changes continuously with A. On the other hand, as we have seen in the above slide, okay, so if you change the size of A, if you make A small enough, the purple curves would describe the entanglement wedge, but if you change them past half the size. The blue ones would describe it. So it can jump discontinuously. Okay, so that's one interesting feature. Okay. On the other hand, the entanglement wedge was a natural bulk region. It was a domain of dependence of some region, of some homology surface. On the other hand, that's not the case for the causal wedge. So if you know everything in the causal wedge, you also know everything in the bulk domain of dependence of the causal wedge, which is generically actually a larger set. It's nested between these two. It's another covariant construct that people don't really talk about. Okay, both of them end on the boundary of the boundary domain of dependence. I forgot to put a subscript for boundary here. And if you take a set of codimension 2 extremal surfaces that are anchored within the domain of dependence of A, well, the entanglement wedge contains all of those, but the causal wedge, of course, doesn't, as we saw for the actual extremal surface for A itself. On the other hand, neither of them contains all the higher codimensional extremal surfaces, like geodesics, that are anchored within this domain of dependence A, don't have to be confined to either the causal wedge or the entanglement wedge. All right, those are just some properties to sort of hone your intuition. All right, so let me now go back and describe two constructions that are related to the HRT prescription. In some sense, the extremal surface you can think of as extremizing in two steps. Well, it's sort of minimal under spatial deformations. If you deform the surface spatially, sort of radially, its area increases. On the other hand, if you deform it by wiggling it in time direction, its area decreases. Okay, if you make it piecewise null, its area would be 0. All right, so you can sort of try to do this as a two-step process. And indeed, Aaron Wall, already more than a decade ago, formulated this as a so-called Maximin prescription, where the entanglement entropy of this region A is given by the following process. So you take A, you take any Cauchy slice sigma in the bulk that ends on A, or actually it only needs to go through, contain the entangling surface of A. Within that Cauchy slice is achronal, so it has a globally well-defined minimal surface within that Riemannian geometry. So you find that minimal surface, but now you maximize. Okay, so this is, you minimize within the spatial geometry, but now you maximize over all possible Cauchy slices. Now, of course, if you were to find the extremal surface, you would never try to carry this out explicitly, because calculating infinitely many, there's a continuously infinite set of Cauchy slices that do the job of containing the entangling surface, and within them, it's a hard job to try to find the minimal surface. But conceptually, it breaks the extremality into two steps, and in fact, as we'll see in a moment, it makes it easy to prove certain statements. Now, you could also go in the other direction, and we have formulated this actually quite recently with Matt Hedrick. You can switch the order. So you can take, instead of taking a codimension 1 space-like slice that goes through the entangling surface, finding a minimal surface within that, and then maximizing over slices. Now we take a codimension 1 time-like slice that contains the entangling surface. Now a time-like slice has as we saw in the beginning of the talk, has a volume maximizing within that space-time, within that codimension 1 time-like surface. There's a volume maximizing codimension 2 surface. And so you can maximize first, and now you can minimize over all these codimension 1, what we call time sheets. Okay, so you can take this time sheet that goes through the entangling surface. You first find the volume maximizing surface, and now you minimize overall time sheets. Okay, so that's a prescription that also, so both of those can be showed to coincide with the extremal surface, but they have different flair. Here, the homology condition, instead of being a spatial homology like in the Maximin, here it's a space-time homology. We say that this timesheet is homologous to the domain of dependence of A relative to the future and past of the entangling surface. In other words, the timesheet has to pass through this entangling surface. And these coincide, but they don't coincide in any cooked up metric. They coincide if you assume that the bulk metric really has the ADS asymptotics, obeys the correct dynamics, bulk-Einstein's equations, and the requisite energy condition, the null energy condition. So here we see that in breaking things down, we're fleshing out the physics in some sense. We're relying on the physics to prove the equivalence here. Now, one way to illustrate the power of having more prescriptions for the same thing is that it allows us more flexibility in how we prove various statements. So for example, I assume you have all seen the strong subadditivity. If not, I'll mention it in the second part of the talk again. It's a relation between the entanglement entropies of various subsystems. So here we have subsystems A, B, and C. We can take the entanglement entropy of the whole union of them or of any subsystem. So here's an entanglement of B, here's of A union B, and so forth. And the strong subadditivity statement is this statement. Again, I'll demystify it a little bit later on. But geometrically, so this was actually proved in the it's a universal inequality that holds for all quantum systems, but the proof in the quantum information context is actually pretty hard. In the holographic context, where you restrict to holographic setting, it's actually super easy. Well, it's super easy in the static context. In Ryu and Takayanagi prescription, where you just focus on the spatial slice, it just follows from this definition of global minimality. So here is how that goes. So if you take the entanglement entropy of the region AB, that's the minimal surface. So remember, in RT, we're just on a single spatial slice. It's the minimal surface that's anchored on AB. Similarly for BC. Okay, so the areas, the sum of the areas of these gives you the left-hand side. But now, because the surfaces being on the same spatial slice intersect, you can cut them and rejoin them like this. So you can consider this surface and this surface. And again, the sum of their areas, which I'm calling the surface alpha, the surface beta, the sum of their areas is giving still the left-hand side. I haven't done anything. But now you notice that that this surface alpha is in the same homology class as the region B. And so its area must be at least as large as the area of the minimal surface in that homology class, which is the thing that gives you the entanglement entropy of B. And similarly for ABC. Okay, so that's it. So this very profound inequality in the holographic context geometrizes, and the statement falls out in a single line. In the static context, now what happens when you have time dependence? Well, when you have time dependence, you no longer have this trick of decomposing the surface into two parts, because this no longer has to be an intersection. So the surfaces don't intersect. They can pass time-like separated from each other, even though they're anchored on space-like separated regions. So we can't use that trick, but we can use a two-step process, which is what Aaron did in his Maximin paper. You observe that there is a common Cauchy slice that includes the extremal surface for B and for ABC, because those are nested. And within that Cauchy slice, both of those surfaces are globally minimal. Now you take the extremal surface for AB, which doesn't lie on that slice, but you project it down by, say, null congruence, and you get a surface whose area I'm labeling by this, but its area projected from AB is, by properties of extremal surface, smaller than the area of AB, and similarly for BC. And now you can go back and use the cutting argument on these projections. And so you get a nested set of inequalities that proves the SSA. Okay, that was a bit fast, but I'm sort of starting to rush through to get to the break within sort of not too much after the hour. But I'll leave you to digest that. Similarly, I'll leave it as an exercise to sort of think through what would happen in the minimax situation. It's again relies on a two-step process, but a different one. Now you take timesheets in the homology class that are not containing both this and this, but intersecting timesheets that contain that correspond to the AB and the BC surface. They cut each other. The timesheets cut each other, even though the extremal surfaces themselves don't cut each other. And now you can sort of formulate a set of surfaces within those cut up timesheets that nest in the inequality. Okay, so again, that takes a little bit of thinking through, but one important thing that it sort of illustrates is that, well, two things. One is it uses a different construct, different direction of doing things. And in particular, the space-time homology condition for minimax as opposed to the spatial homology condition for Maximin is a great advantage, because you might for higher inequalities, there are more inequalities that don't have this fortuitous thing that on the smaller side you have the nesting of the regions. There are inequalities that nothing is nested on, everything is sort of crossing on both sides, and then you can't use this trick for Maximin, but you may still get away with using this trick for the minimax, which is work in progress, but that's the hope. Okay, so it uses a different construct, and therefore it can lead to advantage in the proofs. Okay, but for the proofs to make either of them work, you really need the physical input. So again, here we're going back to the observation that if you have this generic situation where you do need to use some covariant prescription, it requires you to know more about the physics, and therefore explains more about the physics. And the physical input creeps into these two things in a very different way, which is the advantage that comes from having different prescriptions. Okay, but all of these three prescriptions, HRT, Maximin, and minimax, ultimately are about surfaces. Now, there's some drawbacks to thinking about surfaces as characterizing the entanglement entropy. For one, it's sort of a very specific location in the bulk for something that's very sharply defined on the boundary as well. And so you might think that it's sort of somehow over-localized, that that's somehow awkward from the sort of UVIR intuition or scale radius duality intuition. Okay, it's not, but that it sounds a bit strange. You also saw this jump in entanglement wedge location as I deform or continuously vary the surface, the boundary region. Okay, the surfaces can jump because the families of extremal surfaces exchange dominance, which one has smaller area. And you can make these jumps to be arbitrarily large. So if you take the region A, say, composed of many small intervals that cover just less than half of the full boundary volume, and you change any one of these ever so slightly to cover just more than half of the volume, suddenly the other option of these minimal surfaces kicks in, and the entanglement wedge becomes from this pink region to this pink region, which is going from covering to what looks in this conformally compactified diagram almost nothing to almost everything. Okay, so the change in the volume here can be arbitrarily large. Which is a strange thing if you think that, the reduced density matrix somehow is supposed to be dual to the bulk region, either in this pink region or in this pink region. Okay, so it's still true, but that's sort of striking about the surface formulation. And the surface formulation doesn't tell you what is, I mean, it makes you think that, well, maybe there is something special at the location of the surface. That's not true. It's just the area of the surface that's capturing the entanglement entropy. There's nothing otherwise sort of special about the location of it. It's not like there are bits of, information living at that space-time location. And one sort of way of realizing that is that these various inequalities that I talked about, the locations of these different surfaces that come in are completely separated. They seem to have nothing to do with each other. So this surface, even though the proof was easy, the surface construction doesn't sort of elucidate why that worked. So instead, Matt Hedrick and Mike Friedman a while ago formulated the so-called bit thread prescription, which in the Riemannian setting, the static situation, they formulated as follows. So you say there's a flow field V where you maximize the flux of that flow field out of the region A, okay, and that gives you the entanglement entropy. The flow field, you can think of it's a vector field, which is divergence free and has bounded norm. So it's the integral curves of this can be thought of as these threads, these bit threads. And this constraint is that they can't end in the bulk. They have to start on the boundary and end on the boundary. And we're interested in the threads that start in the region A and end in its complement. And they can't get arbitrarily packed together. They're bounded from getting very dense by a Planck area. And so this is actually equivalent to the RT prescription by the so-called max flow mean cut theorem, where you say that you maximize the flow from A by packing them as close as they can get, but what's preventing them from getting even closer is the bottleneck. Okay, so the bottleneck is the min cut, is the minimal surface, and so this gives you the same number as the RT prescription. Now you want to, and I should say before going to covariantization, I should say that this has much more of a intuition building feel to it, because now the surface is more accidental. It's just the bottleneck, but the flow, even though the bottleneck can jump discontinuously under varying A, the flow field doesn't have to jump discontinuously. It can vary continuously. Okay, and you can think of these threads as maybe connecting EPR pairs, one in the region A and one in its complement in some sense. So it's counting sort of the, how many EPR pairs it would take to build up the system. And that's given by this entanglement entropy, okay, for in this pure bipartite setting. So that's the picture. Now this relies on a static configuration, on this Riemannian geometry. So of course we want to again covariantize this, and naively you might have two natural guesses once you reinstate in the bulk space time. Okay, you have, on a spatial slice, you had these threads, these one-dimensional curves. Now you might say that, well, if these are some things that somehow connect, a thread is something that sort of knows about an EPR pair that connects it up. Well, maybe in space-time, since the EPR pair on the boundary lasts for some time, you might have some world sheets, some two-dimensional sheets that get spanned by sort of time evolving these threads. That would be one option, one natural guess. Another guess would be, well, these are no longer located on some arbitrary spatial slice. They can meander in space-time, but they still remain curves. When I started this, I thought, well, it has to be this. But it turns out that that can't work for various reasons, which I don't have time to go into. And in fact, but I'll revisit at the end, hopefully. But in fact, this is the correct picture. And in fact, there are two ways that you can, two sort of dual formulations for one-dimensional quantities whose flux is or fields whose flux is counting the entanglement entropy, and they're so-called Lagrange dual of each other. So this is using Lagrangian duality, where if you have a constraint problem where you have some Lagrange multipliers, the Lagrange multipliers and the actual variables that you're extremizing over exchange roles. So we call them V and U for some historic reason. The V is what was the generalization of what was the V in the previous slide. You still maximize a flux of some flow field V, but now the maximization is over the full domain of dependence of A, not just A. And the constraints are not just this divergence-free constraint, but a more non-local constraint on the density of these things. It's saying that the projected density along any time-like curve in the geometry has to be bounded. So if you're an observer in the space-time and go through these threads, all that you can encounter in your life has to sum up to less than this number. And it's subject to a constraint that this flow field has to vanish outside of the domain of dependence of A and domain of union domain of dependence of the A complement. And in any flow that implements the maximum here, it turns out you can prove that this flow is collimated through precisely the HRT surface. So we didn't put it in by hand, it came out from the mathematics. So here is just a slice, the Clutter thing slice of the soup can picture, where the domain of dependence is just, looking at sideways, just this time-like segment here, similarly with domain of dependence of A complement. And this flow V goes, whose integral curves are these green things, goes from A to A complement. You pack as many of them as you can going through the space-time, but as many as you can reproduces precisely the area of this HRT surface. Now the U threads are, as I said, a dual of this. Now we are going to minimize over another flow, which is actually going to be time-like, like this. Okay, so these are time-like threads, which are still divergence-free, but now whose density is, again, has this non-local bound, but is bounded from below rather than from above. And it says that any spatial curve that goes between A and A complement has to have at least some number of these. Okay, and again, now U is 0 inside A and A complement and has to be, and can be non-zero everywhere outside. Okay, so these threads pass from the past to the future, and you want to maximize them, you want to minimize them subject to the lower bound. So in some sense, you can think of these still as sort of joining EPR pairs. And in similar spirit, this you can think of as sort of disentanglers. So you can ask how much entanglement could you extract out of this, or how much should you disentangle to break up the correlation, the entanglement completely. All right, so these are different pictures. And in both cases, the HRT surface comes out. They give rise to a completely different types of prescription. And again, you can try to utilize them to have completely different flair to the proofs. Okay, so I am hour into the talk, so I will now pause for the break. And in the second part, I will go to talk about the multipartite entanglement. But before taking the break for 5 minutes, let me again pause for questions. Okay, so good. So now let me come back. Okay, so this is now the second part of the talk. So I'll switch gears. And although I was talking all about this time dependence and so forth, I'll now mostly be focusing on what happens in the context where I can use just the RT. And I'll talk about what happens when you have multiple subsystems, as we already saw a preview of with the context of strong subadditivity. And I'll define for you a convenient sort of characterization of how to deal with the entanglement entropies of having of multiple such subsystems. I should say multipartite entanglement refers more than just a set of entanglement entropies for all sorts of possible partitions, but knowing the bipartite entanglement, the entanglement entropy, now for all possible subsystems, actually does tell us quite a lot of useful information. So this is the context I will still be sticking to. All right. So
sorry to interrupt. Can I ask one more
okay.
question? So
Yes, please go ahead.
what we are talking about here are really the quantum properties of the boundary theory, right?
Correct,
But,
correct. The
when
entanglement
we,
entropy is all defined in the boundary theory.
yeah, but somehow like we are assuming the null energy condition and so on and so forth in the bulk. So we are totally looking at classical properties of the bulk. So
Correct.
is it like, I mean, can you give an intuition for why the classical properties of the bulk are able to capture the quantum properties of the boundary theory or something like that?
Right. So that's the beauty. That's sort of the thing that we're after trying to understand better. But that's the beauty that's the miracle of the ADS-CFT correspondence. Somehow the bulk emerges. It has this, more space-time dimensions and so forth. It emerges from the boundary theory. The boundary theory is strongly quantum. And yet the bulk manages to be classical. So all these genuinely quantum quantities like entanglement, which is, quintessentially quantum object, actually gets captured by something that's entirely classical. The entanglement entropy got characterized by just an extremal surface in a classical bulk geometry. So somehow in that correspondence, in that mapping, we had this miracle going on that, entanglement entropy is, difficult construct. It's a very fine-grained quantity that's very sensitive to the state of the system.
Yes.
And yet, well, and the holographic map is also very complex thing. The space-time gets completely scrambled and so forth. And yet, combining those two things, you might think it's completely hopeless to have any sort of bulk dual of entanglement entropy, but it turns out to be described by just about the simplest possible thing you could envision, namely area of an extremal surface. Okay, so there is something that's one of the first hints that there is something profound in this connection between the boundary entanglement and the bulk classical geometry. Okay, so that the bulk, that the geometry builds, that the entanglement builds the space-time. But we don't have a very clear way of saying what's underlying that, what's the machinery really in this process. And this is this is sort of the motivation for these explorations. One wants to understand, okay, if one understands what is the entanglement structure of the CFT states that correspond to a classical bulk dual, well, then one might learn what aspect of the entanglement is responsible for the classical bulk geometry, as opposed to, for example, a superposition of multiple geometries, or something that's definitely not classical.
Thank you.
Okay.
Thanks a lot.
Thank you. Okay. So entanglement entropy, if you have some state in the CFT and you specify some subsystem, let's say some spatial region A, so you bipartition the Hilbert space into part that sort of knows about the A and everything else, you can formulate the reduced density matrix, which is sometimes called the marginal of the full density matrix, as by tracing out over everything that you don't know. Okay, so over a complement. And then the entanglement entropy of this subsystem is simply the von Neumann entropy of this reduced density matrix, okay, which is in a sense a measure of mixedness of this reduced density matrix. How much is this density matrix correlated with the, is A correlated with the rest of the system. Now, you don't have to consider just single system, you can consider multiple systems. So here we take a spatial slice of the boundary, just a space, and we can partition that space into multiple regions, as we have already been doing in the first part, but not just A1, A2, but A, B, C, D, whatever, and call the rest of it to fill up the remaining space. I'll call that O, and you can think of each of these subsystems as having its own Hilbert space, and you can think of the remainder as the sort of the purifier. There's a pure state on this full, if you have a single boundary CFT on the full boundary. And now you can formulate this entanglement entropy for any of these regions, but also for the composite ones, for A, B, for AB, and so forth. And these are independent. They're constraints, but they're independent. They give another dimension to the what set of entropies you can have. And so you can collect all of these numbers into the so-called entropy vector in entropy space, whose dimensionality depends on how many parties you started with. It's for each party, you can either contain it or not contain it in your entanglement entropy. So that's 2 to the n, but we remove the empty set. So it's 2 to the n minus 1 dimensional space. So that's the entropy space. And in that entropy space, the numbers corresponding to the subsystem entropies can be collected into the entropy vector in this entropy space. So for n equal to 3, you have just A, B, C. So you can have these 7 distinct entanglement entropies. You have a 7-dimensional entropy space. Now, in general, we want to understand arbitrarily many such subsystems, because after all, the boundary is living on a continuum space, so you can have arbitrarily refined partitions. And there is nothing fundamental about fixing n to be 3 or to be 5 or whatever. Okay, so what we want to do, of course, the bigger the n is, the bigger the dimension of the entropy space is. So and actually there are many constructs in this that grow doubly or even triply exponentially. So things get hard very quickly. But nevertheless, what we want to do is we want to sort of abstract away from all this things that are independent of how many things you partition the system into, and think about the structural relations between the different values of n, okay, between how many partitions you have. Now, not every such entropy vector is possible. Only certain types, because they're restricted by various physical statements. So one we have already seen, but the more primal one is the so-called subadditivity, which is saying that the entanglement entropy of, sum of entanglement entropies of 2 separate systems must be at least as large as the joint entanglement entropy, which you can think of in terms of the quantity mutual information, which is just the difference between these two sides, which counts for you the total correlation between A and B, that quantity cannot be negative. Okay, so it's positivity of mutual information. The inequality that we have already seen is the so-called strong subadditivity, which is saying, which if you write in terms of this mutual information, is saying that if you take the mutual information between A and say system BC, that must be at least as large as the mutual information between A and B. In other words, so this is collected into something called the conditional mutual information, and the subadditivity is the statement of monotonicity of the mutual information under inclusion. Again, that's eminently sensible. If you have some amount of correlation between 2 systems, if you enlarge one of them, well, the amount of correlation can't decrease because you already had the correlation from the smaller one to start with. Okay, so both of these, SA and SSA, are properties of universal properties of quantum systems. Here we have specified only 3 partitions, and you get more such, well, you might get more such universal relations when you increase n, but in fact, we don't know any other universal ones for larger n, but we know, and I should say, when I say how many there are, you can, of course, relabel these parties. Okay, so you also have one for SA plus SC is greater or equal to SAC. And you can think of the purifier democratically with all the other subsystems. And if you use the fact that entanglement entropy of a subsystem is the same as entanglement entropy of its complement, this subadditivity transforms into something that would be, well, for two parties is a looks like this. It's something called the Arkelip inequality. Okay, so by each of these, I mean the whole family under the permutation and purification symmetry orbit. Okay, so they're families of all of these, but they're more with larger n, but also further restrictions if you restrict the system. So in particular, if you consider just CFTs that are describing classical bulk geometry, so you restrict to geometric states in holography, we want to understand what are all such relations that restrict where the entropy vector can live. That's restricting the entanglement structure of geometric states in holography. Now, in the entropy space, you can think of this as, well, you can coin a set, a region in entropy space, which happens to be a convex cone, as spanned by the all allowed entropy vectors. Okay, so you collect all of them and they form the envelope of them is some convex cone in entropy space. And when you restrict them to holography, that's what's forming this holographic entropy cone. I'll abbreviate it by HEC, holographic entropy cone. That was coined already almost a decade ago by this group. And so, for example, if you have two subsystems, A and B, and then the complement, the purifier, the entropy space is three-dimensional. It has an axis for S of A, axis for S of B, and axis for S of AB, or S of O, the purifier. And we have the subadditivity saying that S of A plus S of B must be at least as large as S of AB. So that's this purple plane that I have cut off here, the purple plane in this space. And the inequality says that you have to be below that plane. These purifications are just in this simple setup, just rotations here. So these Arkelipes are similarly saying that you have to be above this plane and above this plane. And so the intersection of all these half spaces spanned by these facets are forming this cone for us. But there you can equally characterize, instead of characterizing the cone by the facets, by these entropy inequalities, you can also characterize it as a convex hull of these extreme rays. So while the facets were codimension 1 hyperplanes, the extreme rays are just one-dimensional objects. And any conical combination, any positive combination of them is a vector that lies inside the cone. So these extreme rays correspond to entropy vectors of very special states that can be expressed as sort of combinations of any other states. So as we'll hopefully see a little bit later, you can think in this particular instance, this ray corresponds to the EPR pair, to a bell pair between the A and B. This one would be bell pair between A and O, and so forth. Okay, so these special states are giving us entropy vectors which are extreme rays of this cone. In fact, for n equal to 2, the holographic entropy cone is the cone that's also the same as the set of entropy vectors that are not restricted by holography, but are restricted by any, have to be entropy vectors of some quantum system, so the so-called quantum entropy cone. And in fact, it's the set of vectors that's specified by specifying all the subadditivities, that so-called subadditivity cone. Now, in general, all these cones are for higher n. If you refine the specification of subsystem into more than just A and B, these cones are all separate. Okay, so we can define this or sort of consider these separate cones in the entropy space, and they form a hierarchy, a nested structure, which is, further and further, the bigger and bigger gaps between how much nested there are as you increase n. The holographic entropy cone is defined by the set of entropy vectors that are realizable holographically for some geometric state in some holographic CFT. The quantum entropy cone is the set of entropy vectors that are just physically realizable, just subject to quantum mechanics, not restricted to only the holographic CFTs that describe classical bulk geometry. So that's a larger set. The sub-additivity cone is the one that it just says that the entropy vector is compatible with all instances under permutations and purifications, all instances of all these sub-additivities between any pair of subsystem. Okay, so that's the largest cone that we'll consider. And it's the most primal one. It's just the one that doesn't put in any physics except for the declaration that the amount of correlation cannot be negative. That's it. Okay, so physical subsystems restricted further by, for example, strong subadditivity. So this cone contains plenty of entropy vectors that are not physically realizable. Okay, but it's nevertheless, it's the most primal construct. So I have done this as a cartoon. The cartoon is just some two-dimensional slice, and the only thing you're supposed to take from this cartoon is this nesting, and the indication that both the sub-additivity cone and, it happens, the holographic entropy cone are polyhedral cones. They have finitely many facets and finitely many extreme rays, whereas we know very little about the quantum entropy cone. That doesn't necessarily need to be polyhedral. It can have, in some sense, infinitely many facets. We don't know. We just don't know about it. All we know is that it's nested between these two. And in fact, you can find a more refined hierarchy of these cones. So at a fixed n, if you fix n, entropy space is 2 to the n minus 1 dimensional. In that entropy space, there's this cones, and they have this hierarchy, and you can find more. So for example, if you set all entropy vectors that are compatible not just with subadditivities, but also with strong subadditivities, well, that would lie somewhere between the quantum entropy cone and the subadditivity cone, because you're putting more restrictions. So the allowed vectors, the space of allowed vectors shrinks. On the other hand, you can consider just the convex hull of the extreme rays of the subadditivity cone that are realizable holographically, so that are within this holographic entropy cone. So the convex hull is going to be of holographic entropy vectors, is going to be within the holographic entropy cone, but it need not be that all these subadditivity cone extreme rays coincide with the holographic ones. So that's a set that's inside the holographic entropy cone, and so forth. So you can sort of play with these different cones, and using the entropy space as an arena for that is a very useful construct. Okay, but we'll momentarily see that actually we can simplify things even further. You see, what we have done here is we started out with some bulk geometry and some state. Okay, that's sort of continuously infinite specification already. And on top of that, we specify the subsystems A, B, C. That itself is, you specify the shape of the regions and position and so forth. There's a lot of continuously infinite information. But from that, we're abstracting object that lives in an entropy space. Okay, so it's just a vector in some d-dimensional space. That's a drastic simplification to talk about entanglement structure. But we'll see in a moment that we can go even more. We can just start talking about objects that are not a collection of d numbers, but rather a binary 0 or 1 choice for some number of binary choices. That number will be exponential in n, larger than the number of dimensions of entropy space, but nevertheless it's just binary. It's just bits rather than numbers. Okay, and that comes from actually realizing that this holographic entropy cone is intimately related to, can be described in terms of the subadditivity cone. And that's the thing that I want to explain in the rest of this talk. So, okay, I already said this part. Now, if you have the entropies, you can construct the mutual information. The mutual information satisfies, as we have seen, positivity and of course also monotonicity. But the positivity is the one that's the one that is defining this subadditivity cone. It just says that the facets of the cone are saturating the subadditivity inequality, where some mutual information between two systems is zero. And what does that mean? When the mutual information between two systems is zero, that means that their marginals of A and B actually the common density matrix factorizes. So the marginal for AB factorizes into one for A and one for B. The systems are completely decorrelated. Okay, so the phrase marginal independence is just saying that there's a lack of correlation. The mutual information vanishes. And so marginal independence geometrically means that you're on a facet of the subadditivity cone. All right, now what does it mean holographically? Holographically, well, we already saw this in the RT prescription, the slice of the entanglement wedge, this homology region, is connected in the situation where you have a surface for the joint subsystem that's different from the surfaces of the individual subsystems. When that is the case, generically, its area is going to be different from the area of the other option. And therefore, the difference between the areas, between the entanglement entropy of AB and the sum of the entanglement entropies for A and B is going to be non-zero, is going to be positive by construction. And so we can see that the entanglement wedge between A and B, the joint entanglement wedge of AB, is connected when the mutual information is non-zero, but generically, modulo the phase transitions when these things exchange dominance, generically, it's disconnected when the mutual information is zero. Okay, so the statement of which subsystems are correlated and which are decorrelated in the bulk translates to the statement of which entanglement wedges are connected and which are disconnected for these joint subsystems. And it will turn out that in fact, this whole complicated structure of this facets describing the holographic entropy cone actually can get distilled into just asking what's consistent about the connectivity of these entanglement wedges. So we can formalize that into the so-called pattern of marginal independence. We specify out of all the possible pairs of disjoint subsystems, let me just call them X and Y. X could be, let's say, AB, and Y could be C or something. Okay, it's some composite subsystems that are disjoint. For which such pairs does the mutual information vanish, meaning which ones are decorrelated? And for all the others, the assumption is that they're correlated. The mutual information is positive. Okay, so holographically, as I said, this just specifies which entanglement wedges for XY can be connected and which are disconnected. So the saturation of mutual information, that's an inequality, which a saturation is equality. In the entropy space, each such equation specifies a hyperplane. Okay, so this whole collection of such saturating equalities, this pattern of marginal independence, is intersection of all these hyperplanes. And so it's some linear subspace of this entropy space. In fact, it's a phase, we'll define it in a moment, as not just any subsystems, but only ones that could physically be meaningful to consider, or rather this collections that are physically meaningful to consider. We'll soon see that this linear subspace is in fact a subspace that's spanned by a phase not facet, but a lower dimensional face, or not necessarily a facet, lower dimensional face of the sub-additivity core. And so this is a discrete structure. Technically, in mathematical parlance, it would be a finite hyperplane arrangement. Okay, but don't worry about the technicality so much. One observation is that the more of these saturating, of these decorrelated systems you have, so saturating assays you have, the simpler the system is. And now this gives me an excuse to introduce for you a visualization and distilling of the entropy vector from the spacetime into something that has a discrete structure, not quite yet the binary structure of what I'm after, but just a discrete structure, which is the so-called, well, which is captured by simply a graph. So this is something called the holographic graph model. So this will be a detour, which I'll use partly to give you another sort of piece of what has been going on in what has been an important part of the toolkit, but primarily to illustrate the point of visually illustrate the point of how things simplify when systems decorrelate. Okay, so let me first tell you what this holographic graph model actually is. Okay, so we're distilling discrete information from the holographic configuration that suffices to give us the entropy vector. And this was already coined in this holographic entropy cone paper. So here's the prescription. So you start with the full state and some specification of subsystems on the boundary. That has some bulk dual. In that bulk dual, the state specifies the geometry, the geometry specifies all the HRT surfaces. Here we're only considering the static situation, so these are RT surfaces. And they partition the bulk space into these cells. So to construct a graph, for each such cell, you draw a vertex, and you join the vertices that are corresponding to adjoining regions. So like this B is adjoining to the cell that's just next to it, and so there would be an edge here. But A and B regions are split by these other two, so there is no edge between these two. Okay, and to each such edge, you can assign an edge weight, and the edge weight corresponds, let's say edge weight to this edge corresponds to the area of this RT surface. Locally inside, you can have edge weights. If you have more such partitions, you could have edge weights that are just pieces of RT surfaces that don't even have to go all the way up to the boundary. Okay, so each edge gets its edge weight. And now there's a prescription. Now you can just look at the graph and compute the entanglement entropy of a given subsystem, let's say A, by computing the so-called min cut in the graph, the cost of the min cut. You take all the collection of cuts, meaning you include the vertex for the subsystem you're computing, in this case A, and you include any number of bulk vertices, and the cut is you count the edges that go between what's in A and what's outside. So there could be a cut of this edge, or cut of these two edges, or cut of these three edges, and you take the one with a minimal weight. Okay, so that reproduces for you the entropy vector. If you have two RT surfaces that intersect, you get graphs with these cycles, but you can also consider graphs without cycles. And these graphs can get arbitrarily, but not arbitrarily, but quite complicated. So let's say you take a two-dimensional space. This is a space. You take 4 subsystems, regions A, B, C, D, and you take them to be fully correlated. So you take them close enough to each other such that the RT surface for AB would be an arch sort of in the bulk between A and B, rather than, let's say, individual domes for A and B. And they're pairwise correlated by that. So if you draw a graph model for such a thing, it's a complicated one with many vertices and many edges, which corresponds to the various intersections of these. Let's say there's a point which is inside the ABC entanglement wedge, but outside of the AC entanglement wedge, and outside of the AB1 and BC1 and so forth. Okay, so each such specification gets a point here. Now, once you start moving these regions apart, that will decorrelate them. So if you decorrelate them pairwise, let's say you first decorrelate A from B and then decorrelate it from C and so forth, what happens to the graph in the successive decorrelation is that it simplifies. And eventually, if you decorrelate sufficiently many regions, the graph is very simple. So in fact, you can decorrelate sufficiently many to get a graph that corresponds to a pattern of marginal independence, this linear subspace, which is just one-dimensional, which is the thing that will actually give us an extreme ray of the subadditivity cone. So this was all just a visual representation of what we're ultimately going to be after. It's a very simple notion of implementing, of understanding this marginal independence, how much can things be decorrelated from each other before they trivialize completely. All right, so let me contextualize this a little bit. What is the problem that we're specifying? And then explain why is it relevant for the holographic entropy core. Now, a hallmark of quantum mechanics or entanglement is that if you know everything about the full system, it doesn't necessarily mean that you know anything about the subsystems. That's the point. That's the sort of what Schrödinger found the most perplexing part about the entanglement, and that sort of, in some sense, Einstein thought of as spooky action as a distance. You know the full system, but that doesn't mean that you know anything about its subsystems. Here, we want to ask the opposite question. Suppose you do know everything about a subsystem, but how does that restrict the full system? Okay, and this was already sort of worried. I mean, this question was a deep one and much thought about in the just quantum information context, and goes under the name of quantum marginal problem. Suppose you know the collection of these reduced density matrices, these marginals, maybe not for all possible subsystems, maybe for just some collection of them. Now, does there exist a full density matrix for the full system such that when you trace over A complement, you would get this marginal, this reduced density matrix. When you trace over AB, you would get this one. When you trace over AB complement, you would get this one. When you trace over BC complement, you would get this one, and so forth for the full collection. Does there exist such a density matrix? This is actually a very hard problem. It's computationally very hard. It's in a class that's related to NP-hard problems. So of course, that's not going to be solved anytime soon, although there are offshoots of it which are simpler. We will retreat a little bit more, well, a lot more, and still retreat further. But one step of retreat is, instead of considering these full matrices, reduced density matrices for subsystems, let's just consider a single number, their von Neumann entropy. But let's consider it for all possible subsystems. In other words, let's consider an entropy vector. One can ask, does there exist a density matrix that realizes this entropy vector? In other words, whose marginals have von Neumann entropies that are entries of this vector. Okay, that's a question of realizability of the entropy vector within a given subsystem. Now, we don't know how to solve that problem either. That's still very hard. Holographically, we might have some shot at. If we could construct, for example, a graph given an entropy vector, can you construct a graph model that implements that graph, that entropy vector? Okay, I think that's much easier, but we don't know the answer yet. We don't have the prescription to do it yet. So we'll retreat even further. We'll retreat into this marginal independence problem. Marginal independence problem is not worrying about how much things are correlated, these actual numbers going into the entropy vector, but only whether they are correlated or not. It reduces things to binary rather than, real numbers. Okay, so given a pattern of marginal independence, given a specification of what is decorrelated, does there then exist a density matrix and some configuration that implements it? Okay, so this pattern of marginal independence is this binary specification. If there exists one, then if there exists a density matrix that implements it, the specification of when such a pattern, for what patterns this is possible, is the marginal independence problem. If you say what pattern is possible in quantum system, in quantum mechanics, that's the quantum marginal independence problem. If you restrict to holography, that's the holographic marginal independence problem. Okay, so that's sort of just a specification of a problem. Now, why am I fussing about this pattern of marginal, of marginal independence? Why can't you have just anything? Well, you can't have anything because either there's some mathematical inconsistency or there could be a physical inconsistency. For example, because there are many more mutual informations than the number of dimensions in the entropy space, there are linear dependencies between them. There are these relations. So this is just an identity. If you write this out in terms of entropies, this is an identity. But that means that if you specify that 3 of these are 0, there's no chance that the pattern of marginal independence could have this one non-zero and be realizable, because that would violate this mathematical identity. Okay, so that would lead to an inconsistency. So such a pattern of marginal independence would be manifestly bad. There could also be physical inconsistency. For example, by subadditivity, you know that each of these is non-negative. So if 2 of them on one side are 0, that means that, well, the other side is 0, but because they're non-negative, it can't be a positive one and a negative one to balance out. So they must both be 0 individually. So subadditivity would imply that if these are in the PMI, so must these 2. Strong subadditivity violation would be yet another physical inconsistency. If you have A decorrelated from BC, well, it must be then decorrelated individually from B and from C. Okay, this is in fact a weak condition than strong subadditivity, because strong subadditivity tells you about the numerical values of these, or relates the numerical values of these. Here we're just, again, saying the binary thing, and we'll call this the Klein condition. Okay, but that's something that's necessary for realizability of this pattern of marginal independence. And you can organize these mutual informations by giving them ordering that's particularly convenient for implementing this Klein condition as a poset where you include I of A, B inside is sort of related to, is less than in this poset structure than I of A, B, C, because B is contained in B, C and A is contained in A. Okay, so you can see this visually by a Hasse diagram for an example for n equal to 2. And this type of thing is very restrictive. So the linear dependence ensures, the fact that you satisfy linear dependence is implemented geometrically by declaring that we're only considering patterns that are spans of this phase of subadditivity cone, which is a specification of all of the ones that are mutual informations that are 0. And the Klein condition gets approximated, which approximates SSA, is implemented as a downset in this MI poset. And that reduces the patterns, the possible a priori patterns, very drastically. So if you ask how many total faces of various dimensions there are of the subadditivity cone, and how many of them satisfy this Klein condition, there are fewer of them with a Klein condition, and this gets much more drastic as you increase n. Okay, so that was one sort of detour into what is the this marginal independence problem. Now, why do we care? The point is that you can actually use this to reconstruct the full holographic entropy cone. So this is a paper from a few years ago that utilizes graph model, and I'm running out of time, so I'm going to completely sort of skip over this and just get to the statement of the actual theorem. the theorem, which assumes a certain conjecture about which we have strong evidence for about how to describe extreme rays of a holographic entropy cone graphically, that they can be described by so-called tree graphs. Assuming that conjecture, one can prove that any extreme ray of the holographic entropy cone for some n parties, you can obtain from extreme rays of the subadditivity cone, but for more refined party, not necessarily the same one, some further refinement, by projecting them down in a certain way. Okay, so let me show you a cartoon of what this looks like. Here I have drawn slices of various entropy spaces organized by number of subsystems that I want to specify. And these are the cartoons that are supposed to have been harking back to sort of this picture, where we have taken a slice of the cone for some n, and we delimited on it where is the holographic cone, where is the subadditivity cone. Okay, so here we're taking all of these for different n. For small n, for n equal to 2, the subadditivity cone coincides with the holographic entropy cone. For larger n, it doesn't coincide, but all its extreme rays that are holographically realizable for the subadditivity cone are extreme rays of the holographic entropy cone. Then at n equal to 5, you start finding extreme rays of the so the holographic entropy cone is this thing bounded by this orange region. You start finding extreme rays of it that are actually not extreme rays, well, like this one, that are not extreme rays of the subadditivity cone. Okay, so the convex hull of the subadditivity cone extreme rays that are realizable holographically is smaller than the holographic entropy cone. That's the last nesting we talked about on the slide where I was showing making this comment here. Okay, so that's implemented for 5 parties, but it turns out that if you take a more refined system, the subadditivity cone of that more refined system would have an extreme ray that projects down to this one. And maybe another one, you would need a higher refinement, but then if you consider sufficiently high refinement, you don't have to consider any further refinements. All the extreme rays of the holographic entropy cone are projected from some extreme rays of the subadditivity cone. Okay, that's what this theorem was telling us. And so this in principle will allow us to construct the full holographic entropy cone for any n. Now in practice it's complicated, and but it demystifies the entropy cone. And the crux is then, how do you characterize the set of subadditivity cone extreme rays that are realizable holographically, which is precisely coming from the solution of this holographic marginal independence problem. In fact, a specification to it to just one-dimensional PMIs, which is what we call this extreme holographic marginal independence problem. All right, so since I'm running out of time, I'm going to skip all of this part, okay, and I'm going to do make one more comment, which is that if you want to go from extreme rays to facets, that's itself a computationally hard problem. But the facets are the things that are the holographic entropy inequalities that are specifying what the holographic entropy cone is, and they're complicated. So we already saw the universal ones. There's the first one that comes up for 3 parties is this so-called monogamy of mutual information. And in terms of entropies, it has this form. You can think of it as tripartite information being non-positive, being non-positive. And actually, it makes the strong subadditivity, which was very important in the development of this field, actually redundant, because you can obtain this from the sum of these two. So it's graphically, if you think of these being the subadditivities, these the strong subadditivities. This monogamy of mutual information is a hyperplane in the entropy space that cuts off all the strong subadditivities. And what we want to know is the collection of all such sort of non-redundant relations for higher n. Okay, for n equal to 4, we have more facets, but still composed of just subadditivities and MMI. For 5 parties, we have we have 5 more orbits, which take much more complicated form, and this gets harder and harder for larger n. And one wants to ask, how do we systematize it? And how do we package these inequalities? So remember, these are the things that result from knowing the cone, which we already, in principle, can define from the extreme race. And here's a simplification that I just want to flash as another direction, another progress that happened in the last year or so. You can repackage these inequalities in terms of multipartite informations. So multipartite informations are specific collections of entanglement entropies. Mutual information is multipartite information, which is bipartite. The tripartite information is you add all the entropies of the single system, subtract all the ones for double systems, add the one from triple systems, and this continues for all the multipartite informations. And you can then take composite arguments here. Say replace C with CD and substitute into this basic formula. But if you have these single systems here, that collection actually forms the basis of the entropy space, which is in some sense more convenient to deal with than the basis in terms of the entropies. And in fact, you can consider conditional multipartite informations, and from them you can consider collections of tripartite information. So here is when you write an entropy inequality in terms of the I basis in some shorthand, so it's better packaged. But the best packaging that we have come up with is what we call the tripartite form. You take conditional tripartite informations and use some terms only of this form and nothing else. And it renders these inequalities to be even more compact. And in fact, this compact form allowed us to generate a whole bunch of new inequalities. Okay, I don't have, again, I'm out of time, so I'm not going to explain what all these things mean, only to say that this seems to be a very convenient packaging. Okay, let me now skip over this, and let me just end, because I have only 2 minutes left. Let me just end with some sort of step back and ask what have we learned. So from covariance, the most important thing is that, well, it allows us to extract the physics more than situations which have lots of symmetry, because it sort of breaks the degeneracy between seemingly degenerate or similar constructs, as we saw in the example of causal wedge and entanglement wedge. But there are many more such examples. So it manifests this physics. And for example, people have the tendency of associating things like, the extremal surface area with prescription with a black hole entropy prescription. The black hole entropy is given in terms of its horizon area. The horizon is an extremal surface, but the slice of the horizon is an extremal surface. And so you might think that, well, maybe if you take entanglement entropy in time-dependent setting, well, maybe it should behave in some sense like black hole horizons under time evolution. That, I think, is misguided, because black hole event horizons really are fundamentally codimension 1 null surfaces. Entanglement entropies are areas of these extremal surfaces. The extremal surfaces are codimension 2, and there isn't a natural association from, entanglement entropy of some region A at one instant and for the region at another instant. Those are different surfaces, but they don't need to have a continuity in time in any sort of similar way as a black hole would. And so, adopting a lesson that, well, there's a similarity between black hole area entropy prescription and the RT prescription, uplifting it to time-dependent context may well be misguided. Okay, so this is the sort of thing that fleshing out the generic situation allows us to realize. And there is a window of opportunity here because the bulk was utilizing these codimension 0 regions even for constructs in the boundary that pertain to a single time. Entanglement entropy of some region A at a given time utilizes this entanglement wedge, which is a codimension 0 bulk region. But if you take one at a later time, there's another codimension 0 one region, a bulk region that overlaps with the first one. And so the bulk very efficiently is precisely sort of put together in such a way that it makes all these overlapping, all these entanglement entropies that correspond to overlapping regions consistent with one another. This is not something that quantum information from the start implements. It's there, it emerges, and this is a feature of the bulk that's manifest there that we haven't used in the QI. So the window of opportunity is to sort of utilize that, utilize the covariance to see what restriction that poses on the quantum information quantities to understand how it actually builds space-time. From the multipartite entanglement part of the talk, we learned that this abstraction all the way down to this binary information of what is the pattern of correlation and decorrelation, that's extremely powerful. And so it allows us to reconstruct this holographic entropy cone and so forth. But here I want to pause and stress that the subadditivity cone is very universal. It has no idea about holography. It's a universal statement. So where does this bulk emergence even come from? It comes from, well, there are three ingredients. One is we're only considering the set of extreme rays of the subadditivity cone that are holographically realizable. But what does that actually mean? Well, one thing is that it allows us infinitely refined partitions, so we can refine the subadditivity cone arbitrarily, and classicality. So the important machinery here was this phase transition. This phase transition was the exchange of dominance of the surfaces that we could abstract everything to the type of question of, is AB surface, HRT surface, composed of the A HRT surface and the B HRT surface, and so forth. So this abstraction was there only due to this classicality. And there's many ways that you could generalize this. You could talk about, we already have time-dependent, arbitrarily high-dimensional bulk space-time, but we can change the asymptotics. Or you can go beyond the classical space-time and ask about stringy and quantum corrections. You can ask about other entanglement measures. And in fact, much of the subject is developed in some discretum, some finite dimensional Hilbert spaces, but passing to the continuum, as is, suggested by the space-time description, that could be another leap. So there's many generalizations that one can do and lots of exciting progress, but let me leave it at that and wish you to enjoy the journey. So, thank you.